So this will be our integrated workflow for today. No, you're gonna see it on as a live session. No, the integration of TEKLA structures, STAAD.Pro and IDEA Statica and IFC provides a streamlined end-to-end structural design workflow. So first is TEKLA to STAAD.Pro. Structural models begin in TEKLA structures, where geometry and member properties are created. These models are then transferred to STAAD.Pro for loading such as gravity load, wind load, and earthquake load, then to perform advanced structural analysis and design to check the member's adequacy and serviceability. Then STAAD.Pro to IDEA Statica. STAAD.Pro model will be exported to IDEA Statica, enabling detailed connection design, code compliance checks, and capacity optimization. Then from IDEA Statica, so to IFC, designed and verified connections are exported via IFC, or what we call the industry foundation classes, ensuring standardized open and data exchange. Then IFC to TEKLA. No? The IFC file is re-imported to TEKLA structures, where the constructible model is updated with verified connection details and fabrication ready information. And then, so finally, TEKLA model will be the final model to produce drawings, details, and fabrication drawings. No? This integrated workflow enhances accuracy, efficiency, and collaboration, ensuring that analysis, connection design, and fabrication models remain synchronized throughout the project life cycle. And then with that, no, so let's begin with a live demo of the software modeling and integration. And with that, I'm gonna be overing the webinar now to Dennis Acosta. Dennis, ready?
Yes, thank you very much, Engineer JP. And good afternoon, everyone. Wants to, okay, allow. Everybody can see my screen?
Yeah.
Okay, can you see my screen?
Yep. I can see now your screen.
Yes, can see your screen.
Okay, thank you very much. And yeah, to start with this demo, as you can see, this is the TEKLA structure. This is a 3D modeling software and detailing software. So as you can see, you can rotate, zoom in, zoom out, pan. And I will start doing the modeling here. Here I have the elements, steel elements, that I can use to model, let's say, first is column. So I have the profile here. The profile is available in our library, which is there's a rich library of the profile from a different environment. At the moment, we're using the UK environment. And then just simply click the position. And then as you can see, you can get the 3D model object. And this is not just a view, it's an object, because if you inquire this part, you will get all the information that you need. Let's say, for example, this one, you can see the weight of the steel will be shown here. Even the properties of the material will be shown here. Now, if I change this one, let's say I want this one to be a smaller profile and a shorter one, modify. So immediately, if I inquire this element, everything will be updated automatically. So that's how the system works in TEKLA structure. So everything is an object. So again, since we're talking about a 3D modeling software, so I will model this structure in a 3D view. But anyway, anytime if you want to make it as a plane, you can do that one. But I prefer to do that one in 3D modeling. So I will start. I'm going to continue with adding my rafter here. So let's say I have the 6,500 here, then connecting this two rafter. So the size is 356 by 171 by 51, and then pick this beam. And if I want to change this one, the name from rafter to beam, I will just simply load my attributes. You can save your as many as attributes as you want. Now I have the frame here. All I have to do is just simply use my copy command, linear, pick this 2 point, and then put the number of copies, say 5, and there you go. So as you can see quickly, I can do the model of this frame. And then to continue, I can add a connecting beam here from this frame to this frame. Yeah. Or I can just use my copy command. So put this point and this point. And then if I want to copy this one going up, let's say 6.5, and then copy, and then select again. Then I know that that one is in the direction X, direction Y. Just simply type here 4 copies. And there you go. So now, I have already the full frame with all this beam and rafter. So let's continue adding the bracing. So for the bracing, I'm going to use my beam properties again, but I'm going to choose the CHS 114. So pick the center of the beam and then copy this again from this point to this point. And then I can copy special. So again, pick this point to this point. The reason why I'm picking this point to this point is to get the distance and the direction. And then all I have to do is to type here 2 copies, and you will get all this bracing. Now, to continue, I'm going to add a roof brace, again using the beam properties here, but I'm going to use the rod brace here with a 20 diameter. Just simply click this point and this point, as well as this to this. Now, I can just simply copy mirror on the center of this. All right, and then I can now copy again to the direction of Y. There you go. So as you can see, in a few minutes, I modeled already the whole structure. And then the good thing here is, if I'm going to show you the view on the grid 1, you can see this is the plane view of the elevation. And then the moment that you have the model here in TEKLA Structure, you can easily create the drawing that may use for the design to get the information. Let's say, for example, in this case, I'm going to click the grid 1 and then create the elevation drawing. So here, hit create, and then the system will draw this one for us automatically. So as you can see here, it will create the drawing with the dimensions automatically and also the annotation of the size of this particular profile. And later on, I will come back to you on this one so that we can see whenever we have the changes. So we will see the update on this drawing. Now, I'm done with my, my modeling. So all I have to do now is to go to my analysis and design. And then here, I will open the A&D models. So this is the plugins that we have to integrate the TEKLA structure to the STAAD. So all I have to do is to hit create new, and then slow this one. So you can see there's some options here that I'm not going to tackle. And once I pass this one to my colleague, then he will do the detailed information for the STAAD. So all I have to do is to click OK. And then as you can see here, all I have to do is select this one and then add this selected model. And as you can see, it will create the analytical model from TEKLA structure. This analytical model is the one that will transfer to the STAAD. So at this point of time, I'm going to save my model. Okay, yes. So I'm not going to export this one. I will let my colleague, Engineer Jarrett, to do that one. And all I have to do is to write out, because We're using now the model sharing. This is the TEKLA structure capability. Now I'm here in Malaysia, by the way, and Engineer Jarrett is in the Philippines, and Engineer Jean is in Singapore. So using our model sharing, we will able to see the model that I have created from my computer to their computer, from this country to another country. So now I'm writing out the model. So while I'm writing out this model, so I'm going to call Engineer Jarrett to continue on this workflow or to continue on the STAAD. So maybe I'll just let's wait for a few seconds while writing out this model so that once it's write out, Engineer Jarrett can just simply read in to his computer with this TEKLA structure. Now it's done. So I will pass this one to Engineer Jarrett to continue the work.
Right. Thank you, Engineer Dennis, for the model of the structure using TEKLA structure. So this time, allow me to present my screen. So can anyone see my screen now, please? Any response? Okay, thank you so much for your thumbs up. Anyway, for those who cannot see the screen or the shared screen, or the sound is not actually audible on the respective device, so you may tend to reconnect in order for you to see and heard uh, the entire webinar. Anyway, as Engineer Dennis said, after the modeling of the structure using or in TEKLA, this is the time that I will be fetching in the data from TEKLA structure going to STAAD.Pro and perform some modification and check the adequacy of the steel structure if it is actually passing to the demands or to the loadings that I will be applying later on. Okay, so by the way, here in TEKLA structure, as you can see, that the entire interface doesn't have any structure because I haven't reading in the output coming from Engineer Dennis. So in this case, I will be clicking in this read in icon on the upper part or on the ribbon toolbar of the TEKLA structure in order to fetch in the data which was created by Engineer Dennis. So in a span of few time, we can see here that the most recent structure created will be incorporated in TEKLA structure. Okay? So once done reading in, we can see that the structure here will now be reflected. Okay. So as you can see here, it was modified by my colleague earlier. So when I close this, so we can see the same exact model accomplished by Sir Dennis earlier. Okay. So now, before I export this to my STAAD.Pro, so I will be clicking at least one member, say the rafter here. So when I double click the rafter, or perhaps I'll click the user-defined attributes. Okay, and then see the end condition of this selected member, we can see that there is no value yet for the end condition. So what I'm pertaining for the end condition is the degrees of freedom, which are the actual forces, major and minor shear forces, together with the torsion and the major and minor bending moments. So after later on, I incorporated the result from STAAD.Pro going here in TEKLA structure. So we can see that this rafter will now have its own value for the end condition. Now, in order for me to export this going to STAAD.Pro, so all I have to do is to click the Analysis and Design tab here in TEKLA structure, and then all I have to do is to click the Analysis Model name here, and then I'll click the export tab here in order to have it be exported in my STAAD.Pro. Okay. So again here, I will be, or the model will be transferred to the STAAD.Pro or in STAAD.Pro. So there you go. Allow me to present it here. So there you go. This is now the model which was exported in STAAD.Pro coming from TEKLA Structure. So here I just need to modify some of the design or the model itself. Specifically, for example, the tension rods here were actually intersecting at a certain point. So I need to merge them in order for later on when you tend to design the connection, it is oriented correctly. So in this case, I will be selecting probably the circular tension rod here for me to quickly have it selected and then perform the merging operation in STAAD.Pro.
Selected model.
Okay, so allow me to merge all of this. Okay, and then once done, here in the specifications tab, I also need to delete the initial releases which was incorporated here in STAAD.Pro. So I need to delete the end releases. Okay, and then recreate the releases for the entire structure. So as you can see, all of this are a rigid connection, and I need to incorporate uh, releases. Okay, so in this case, the value of the releases that I will be incorporating or adding is equivalent to 99.5. Okay, so actually my intention here for this certain value is for the reason that if you have the release be applied on the bracing, specifically if you want to change the support condition, the instability warning will be avoided. Okay, so mentioning that the releases will be applied to the bracings, as you can see here, I will be incorporating the releases on the end part of the bracings. And then later on, I will be also adding the tension specification for the tension rod member. Okay, so with that, I will be clicking the beam tab here and then provide the partial moment release value of 99.5%. Moreover, I'll need to do the same thing for the end location. And then the tension specification for the tension rod. Now, for me to easily apply the end releases, so perhaps I'll do first the application on the bracing. So in order for me to do it quickly, so I just need to make it be viewed on the left view and then select the braces here. Okay, because as you know, if there's any overlapping members on a certain view, then those members selected or those members that overlaps will be all selected. So the indication that the release is currently applied is the indication of the blue circles here. At the same time, I need also to do this for my girths, okay? But in order for me to not get confused, I will turn on uh, the icon or the color for my start and end node. So the green color indicates that the node is actually placed or actually indicates that it is actually a start node, while the blue color indicates that it is an end node. So for the start MP.995, I will use my cursor to quickly assign this. So for start, I'll make it be assigned here, 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 and here. And also, I think I can do this on the side here. As you can see, it is very quick to be assigned. Okay, by just using your cursor. Okay. I'll need to do the same thing for the end condition. So I'll need to click the assign, use cursor assign here and then click assign. So I need to apply it here, 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 and also here. And on the other side of the structure. And also here. Now that I have applied the releases, this is the time that I will be incorporating this time assigning this time the member tension specification. So in order to do that quickly or to select my tension rod, so all I have to do is to click the property corresponding to the tension rod and then go back to specifications tab and then click member tension, assign to selected beam, assign, then yes. So there you go. This is now my modified structure, and I am now ready to apply my demands or loadings prior to checking the adequacy of my structure. So this time, I will now be proceeding with the load cases using STAAD.Pro. And for this particular structure, I will be incorporating both both lateral and gravity loads, which comprise of the following: the dead load, roof live load, the earthquake load, and the wind load. And in particular, when it comes to STAAD.Pro, the primary load cases here are as shown. So I have here my EQ positive X, positive Z, negative X, and negative Z, considering, of course, the earthquake in all direction, together also with my gravity loads, dead load, and roof live load, and my other lateral loads, which is the wind loads, which will be applied also on in all directions. Okay, so allow me to do it in STAAD.Pro. So by clicking the loading tab here, all I have to do is to click uh, the load cases. As you can see, there is a default self-weight value here coming from TEKLA Structures. So I need to delete it. Okay, and then recreate the load cases. As you can see, my load cases will commence, of course, with earthquake. So the title will be EQ positive X, and then EQ positive Z, EQ negative X, and then EQ negative Z. Moving on to my gravity loads, dead load. So the title will be DL. And then for my other gravity loads, it will be roof live load. And the corresponding title is RLL. Of course, you may have your own rule for having its name or title here in STAAD.Pro. So lastly is my wind load. So I need to define the title, which is WX positive, and then WZ positive, and then WX negative, and then WZ negative. So all in all, I have 10 basic load cases here, and this time I will now be proceeding on how to incorporate these loads, or what are the values rather of the loads here in STAAD.Pro. So here I will start with the gravity loads. Okay. So as per my practice in design, I always start with the gravity loads, but it doesn't mean that you are limited, or you are required not to start with the gravity loads. So anyway, for my dead load, of course, since this is a steel member and it carries its own weight, so therefore the self weight must be considered in my analysis. Moreover, when it comes to my other loads like the roofing sheet, insulation sheet, and purlins, so as you can see here, I have here a predefined value, but definitely this value should be coming from your governing codes to which or to where country you belong. So if you have a minimum technical specification also from your client, you can use that as a reference when it comes to your loadings. And then when it comes to the purlins, definitely this should be calculated prior to designing of your rafters or event trusses. And then summing this all up, it is equivalent to 0.20 kilopascal. And since this is a member load, I need to multiply it to the tributary width of 5 and 2.5. So as per the discussion of Engineer Dennis earlier, that the spacing of the rafters is actually at every 5 meters. At the same time, with the roof live load, this zero point 0.6 kilopascal is also coming from the code, and I need also to multiply it also to the tributary width as shown here. So all in all, I have 1 and zero point 0.5 kilonewton per meter, and 3 and 1.5 kilometer also for both dead load and roof live load respectively. So now allow me to apply it to my STAAD model. So here I need to click dead load and then click add. Then proceed by having my self-weight be added in my structure. So direction is Y with a factor of -1. Then member load equivalent to -1, and direction is GY. So of course, we know that gravity load is always acting downward parallel to the direction of the or parallel to the Y direction, and also -0.5. There you go. Then moving on to my roof live load. So you don't need to actually close this window. So you can manage to click the RLL here or your other load cases and proceed with clicking the uniform force and have it be incorporated in your STAAD model. So now I have here -3 and -1.5. Now, allow me to apply this starting with the self-weight to the entire structure by using assign to view, click assign, then click yes. Then UniGY -1. So I will apply this to my rafter by using my cursor to quickly assign it. So something like this. Okay. And of course, here on this side. Likewise, for -0.5, I will also do the same manner or the same process, but it is applied on different location of my structure. Okay, so there you go. My dead loads were now or were all applied in this structure. However, for the other gravity loads, I just need to simply copy probably the corresponding member list here below and then paste it with UniGY -3. And then for my UniGY -0.5, I need to do the same thing in order to save our time, of course. Okay, so there you go. This is now my structure applied or the load which now have the gravity loads. So this time, proceeding with the lateral loads. Okay, so proceeding with the lateral loads, specifically for the earthquake loads. So in order for me to define my earthquake loads, excuse me, I need to define my seismic parameters. But this time, the basis of my seismic parameters is actually based from ASCE 7-10. So as you can see here, I have here my spectral accelerations SSN S1, which is hypothetically has a value of 1.5 and zero point 0.5. By the way, the value of the spectral acceleration is actually coming from the spectral acceleration map here in the Philippines. But hopefully, this will be published soon to our local governing code. Moving on with the long period TL, it is assumed to be 8 seconds. And the importance factor of 1.5, RX and RZ, 3.5 and 3.25, respectively, site class D, FA and FB of 1 and 1.5, CTX and CTZ of 0.0488, and X indices for X and Z direction is 0.75. By the way, my references when it comes to the seismic parameters is as shown here on the last column to which part of ASCE 7 you can look for this or you may tend to cross-reference these parameters using this table and section of ASCE 7-10. Okay, so now allow me to apply it to my STAAD model by simply clicking the seismic definitions here and then click add. And then for the type, which correspond to the code that I will be using, so I need to use IBC 2015 or ASCE 7-10 and then apply my parameters based from what I have shown earlier. So for my SS, I will apply it as 1.5 or it has a value of 1.5, S1 of 0.5, TL of 8 seconds, importance factor of 1.5, RX of 3.5, RZ of 3.25, site class D, FA of 1, FB of 1.5, CT of 0.0488. So same value for CTZ. And then X index for both X and Z direction is equal to 0.75. So there you go. After I have my seismic parameters, all I have to do is to click add here. And then take note that this is only the seismic parameters, but I need to define my seismic mass as per the code. So here in STAAD.Pro, you can quickly or you can manage to quickly generate the seismic mass by clicking the mass model generator here. So after you define first your gravity load, so that's actually the reason for me to commence with the gravity loads, because since I'm using STAAD.Pro and it has this mass model generator, therefore the created dead loads or some portion of live loads, if there's any, will be adapted by the mass model, and then I can quickly present the mass model here in my reference load definition. So as you can see here, my dead load value as a factor of 1, meaning to say that uh, the 100% or the overall dead loads will be considered to my seismic mass. When I click generate here, so you can see here that my reference mass model is now generated. But take note, maybe some of you will get confused around here that it has a direction of X and Z, and all of the sign convention for my mass model is now positive. So now actually when you use the reference mass model generator, you can see here that the loading type is actually in a form of mass. So according with Bentley, it is actually it doesn't matter wherein the sign is positive or negative when it comes to the mass. So it is always acting downward based from the direction that you will set earlier for the seismic definition. Okay, and now when you are also wondering why we have an X and Z direction here, so the mass model generator is actually intended for dynamic analysis, where you need to capture also the generated mass for the other direction, not only with the Y direction. So in that case, I will be adding this mass model to my seismic definition by clicking these parameters and then click add, and then transfer the reference mass model to the right side with a factor of 1 and parallel to the global Y direction. And then click add and then close. So this is the time that I will be having or incorporating the certain load cases for my earthquake by clicking add, and then seismic loads with a factor x direction with a factor of 1. And I will not be incorporating any torsional moment for this case because I haven't applied any floor diaphragm for this structure. So I need to click add here and do the same thing for EQ positive Z, and then EQ negative X. So actually, the only thing that will change here is the direction corresponding with the title, and also with the factor corresponding to where direction it is going. So this is -1 X direction, click add, and EQ negative Z, seismic loads, Z -1. Okay. Now, before I proceed with my wind load, so allow me to measure first my structure, the overall height of my structure, and the overall length and width of my structure as shown here, which is 25 and 14 meters. And for the height of my apex, so perhaps I just simply need to click this node, and you can see that the height of my structure is actually measured from the apex down to the level of support is actually equivalent to 6.5. So knowing those dimensions, so I will be incorporating those for the uh, incorporation of my wind load, specifically for the wind load parameters. So here, as presented in my presentation or in my PowerPoint, you can see here the building classification category of 4, which is in accordance with table 1.5-2, basic wind speed of 250 kilometers per hour, exposure category B, structure type is actually a building structure. Enclosure classification, I assume it to be a fully enclosed structure. A topographic factor KZT, I assume it to be lying flat on the ground, meaning to say that the value of my KZT will be 1. or equivalent to 1. And for my wind directionality factor KD, it is equivalent to 0.85 for building structure. Not to mention that the value of KD is also equal for both MWFRS and components and cladding. And also for my gas effect factor, I assume my structure to be fully rigid, but it is actually dependent on the value of your natural frequency. So I assume it to be equivalent to 0.85. But in ASCE 7-10, when you go on this particular section, you can see that there is an equivalent empirical formula if you don't want to use the exact value of 0.85. Now, having these parameters defined, I can have it here in my STAAD.Pro by clicking the wind definitions here and then click add. So I need to define my wind along X with ASCE 7 2010 as my code, and also for the Z direction with the same set of code. Now, I need to define it using the wind definition. So I need to click the generate tab here and then define the category, which is 4, basic wind speed of 250, exposure B, building structure. And then this is actually will be the basis of our value for KZT. So if it is lying on the ground, flat on the ground, you need to click it as no. Otherwise, if it is actually being erected at a on top of the hills, ridges, or escarpment, then you have to click yes and define the certain information here needed. And then I'll need to click apply in order to for my software to absorb these parameters. And then for my main building data, I need to first modify my dimension unit. And then for the building height, it is 6.5. Building length along the direction of the wind. So since this is wind X, that dimension is equivalent to 14 meters. And then the length normal to the direction of the wind is 25 meters. So for the building natural frequency, I assume it to be 2 hertz. But again, in our code, we have different set of empirical equations that you can use to determine the value of natural frequency. It actually depends on the height of the structure, to what material it is made of, and so on and so forth. And even for non-building structure, you have different set of equation also that you can use to define the value of your natural frequency. Moving on, when it comes to my damping ratio, I need to define it as 2%, or assume it to be 2%, enclosure to be enclosed classification, and for my KD, 0.85, and then I'll click apply. Then lastly, building design pressure, windward, and then I'll click use G here, equivalent to 0.85. And then I'll click apply, and then once the graph was changed, so I click OK, and then click add, and then close. And then I need to do the same thing with the type 2 WinZ. So all I have to do is to repeat what I did to type 1 WindX. There you go. So the only thing that will actually change here is the building length along and normal to the direction of the wind. So since my wind is now coming or along the along this direction, so therefore the building length that is being pertained here to by the software is actually equivalent now to 25 meters. 25, and the normal direction is 14 meters. So definitely it just interchange. And then the building natural frequency and damping ratio, it's still the same. So for the KD, 0.85, and then click apply. And then lastly, for my windward forces. So for this example, I only generate the windward direction or the windward wind load. Apply, then okay. So there you go. This is now the time that I will be having my wind loads be defined here in my load cases details. So starting with WX positive, so I need to click wind load here. So by the way, for the type, I have 2 options. So I have 1 regular and 2 regular, which correspond to wind X and wind Z respectively. So since this is wind X positive, I need to define X external here with a factor of 1, click add, and then do the same thing with WZ here. Okay, but since this is WZ, so the type is 2 and then Z external with a factor of 1. Click add. And then for my WX negative, I need to do the same thing also. But this time, the factor will be negative 1. Click add. And then WZ negative, wind load. Hello.
Yes, I can hear you, Jared.
Okay. So yeah. Anyway, when it comes to the WZ negative, I'll click Z external here and type to here and then click add and then close. So now that my structure loads were now completely incorporated. Okay, so I need to modify this to negative 1. Okay. So now, before I have my structure uh, be analyzed when it comes to the adequacy of the steel members, so I need to actually define my load combinations here. So when I click load cases details here and then click add, so I need to click the auto load combination here using ASCE 7-10. My rule set will be the ultimate load combination or the strength design where my live load is less than 100 PSF or 4.8 kilopascal. So I'll click generate loads here and then I'll click add here. So I have here now a total of 50 load cases all in all together with my 10 load cases which was or which were previously added. Now I need to proceed with the design tab and click the load list here. So this time I will be transferring all of my load combinations to the right side. Okay, and then I'll click OK and then define my code here to AISCT 2016, for example, and then define my parameters like the method. So I will be entering the design method of LRFD, add, and then my FYLD value as a default value. And then lastly, for my commands tab, so I will be having my check code command here be added in order for STAAD.Pro to reflect the value of the utilization ratio, which will be the basis for the passing or failing state of my members, together also with or that is also your somehow your hint if that is designed economically or not. So now for my FYLD, I need to assign it to my entire structure. However, for the check code, I will be uh, uh, what do you call this? Not include the tension rod members. So in here, I will be selecting only the frame, okay, except for the tension rods, and then apply the check code command to the entire structure in the absence of the tension rods. Okay, and then before I run my analysis, I will be modifying some of the commands here in my STAAD.Pro because if I run my STAAD.Pro, there will be a set of warnings to be reflected or that will reflect rather here on my analysis output, which is coming from the coming from my earthquake load. So here I will put a perform analysis command here and change command here. Okay, so this is actually a requirement of STAAD.Pro, not a requirement of X structures. And I need to put change here in order for my matrix to be continuously calculated up to my last load combination. So here I will simply need to copy this incorporated commands for all of my earthquake loads. And then after that, since I incorporated the change command here, okay, all you have to take note that another set of warning will be shown later on. So in order to avoid that, definitely you will add here after the end job information the command which is the set NL command. So set NL command here is actually a command wherein if you have your loadings be followed by change command, then it is required for you to put a set NL command here. So the NL value here pertains to the total set of your load cases, including the load combinations. But as I said earlier, the overall amount of your load combination is actually 50, but here it is okay. It is okay to actually have your NL value be greater than 50. But I highly recommend that the value should not be lesser than the overall number of your load cases. So now I need to save it and then run my analysis. So hopefully my structure uh, will pass. Okay. So let's wait for it to be fully accomplished. Perhaps I need to check it here. So I actually canceled it, by the way. So I need to rerun my structure, by the way. As you can see here that we have no set of errors or warnings reflected after I run my analysis. So this time, I need to click the go to post-processing mode to see the value of my utilization ratios. Okay, so I'll need to click utilization ratio here. So as you can see that all of my members is colored as green, indicating that all of those members is actually passing. So, moreover, if you want to see the specifics of the utilization ratio value, then you can go here on the layouts and utilization and proceed with the all tab or even with the failure tab. So as you can see, no failing members were reflected here. So therefore, all of these are actually passing. Now, before I go back to TEKLA structure, there's a thing that I need to modify here on the properties. So perhaps I will be modifying the size of the rafter. So take note, this size of my rafter actually originally came from TEKLA. So now, what will happen if I tend to change this here in STAAD.Pro? Is it going to be reflected in TEKLA structure or not? So that's where what we are going to find out. So perhaps I will be modifying this rafter size to probably I'll use UB 457 by 60. 457 by 152 by 60. So I think this is a reasonable size for that one. And then I will rerun my analysis. So in a span of few seconds, we can see that the analysis will now be completed. Okay, 5 seconds. So probably I'll need to recheck my utilization ratio if it is actually passing or not. As you can see, the color indicated here is actually green, meaning to say that there is no failing members after we change the size of my rafter of our rafter. So now, after I have it be analyzed here in STAAD.Pro, that's the time that I will now go back in TEKLA structure. But before I see the end condition of my rafter, so I need to click the get results here from my analysis and design model. Then in a span of few time, TEKLA structure will adapt, or we're actually expecting for the TEKLA structure to adapt the changes that happen in STAAD.Pro. So as you can see here, we can see that the structure is now changed from originally from 156 356 rather by 171 by 51 to 457 by 152 by 16 that I have performed in STAAD.Pro. So after I accepted all of the members, so this is the time that perhaps I will be clicking the same member that I have selected earlier to see the end condition of this member. So when I click the end condition here, so we can see that earlier we don't have any values for this members. But after we run and get back in the result here in TEKLA structure, that's the time that it is now updated. But it is not yet updated to my colleagues. So that's the time that in this case, after I get in the result, I will save my structure. So after I save my structure and the database has been stored, this is the time that I will click the write out command here on the ribbon toolbar, right? Then the data will now be shared to my colleagues even if we are not working side by side. So I will now be saving it, and it is now starting to write out and creating packets and such. Okay, and in a span of few time, this will now be being read in by my other colleagues, engineer Jean, to perform the connection of this structure. So writing out, there you go. So this is the time that my presentation will actually now ending. So now, thank you for listening. So hopefully you learn a lot on how to perform the analysis and design of this certain structure from TEKLA to STAAD.Pro. So now, I will now be ceding back the floor to my other colleague, Engineer Jean, to perform the design of the connection. So Sir Jean, take it away.
Thank you very much, Engineer Jarrett, and also to Engineer Dennis. So, okay, I'm taking the screen for now. Let me share my screen. Okay, can you confirm, please, if you could see my screen for now? Before I do the demonstration, just need some confirmation that you guys can hear me properly,
Yeah,
as well as you can see my screen as well.
all good, Jin.
Okay, all right, thank you. So before I do the demonstration, Engineer John Paul has already introduced us, so I don't need to bother introducing myself. I just want to say a few words about our company, IDEA Statica, before I do the demonstration. So first of all, IDEA Statica basically is there are two categories in our program. We're not only doing steel connections, but we are also doing concrete connections. So in steel connections, you can do any type of connections for complex or simple connections. You can do anchorings and even framings. For concrete as well, you can basically do any type of shapes or structures, such as diaphragms. And you can even design some beams with openings for concrete. No? And beside that, our applications can link various global structural analysis software. If you have any software of this, what you can see from here, you can say that you can be able to link our program with this kind of software. It can be FAA software, or it can be CAD software like Rivet, TEKLA, SDS2. So you can link our applications for that. So let me just end my very quick slides over there, and I'll go to demo directly. So in that case, if you could see, I'm now there. So let me just quickly turn off my camera so that we have the necessary bandwidth. All right. So here, okay, Engineer Jarrett and Engineer Dennis has already saved their file. So all I have to do for myself is just read in this, what they have done. So I'm now getting the data from them. It takes a few seconds basically. Okay, here. So all the information's probably is here. Okay, let's just wait for a couple more. Okay, just put this away. All right. So, okay, let me just close. So all the changes that they've made, the member sizes has been applied as well by Engineer Dennis and also by Engineer Jarrett. So I'll just close these things, all this information. Now, in order for us to design the connections, obviously we need internal forces, and that was done by Engineer Jarrett using STAAD.Pro. Now, to get that information from him, he already saved that here. So all I have to do is just go to the analysis and design model. And from there, basically, I just click on the STAAD integration, and all those analytical models has already been added. So all I have to do is just open the application in this case. And I'm going to click on open the applications. When I click that, you can, IDEA Statica will open checkbot application in the background. So here I can already see this is already opening. Or I have to just click on continue. Okay. Okay, so here is the application that was done by Jared. All the information as he already provided, but in my case, all I have to do is just rerun the analysis so that it will be captured in my file. From here, it's running program. Now I all have to get all those internal forces, and I click on done. So from here, now that I have everything captured in my STAAD.Pro model, so all I have to do now is I can transfer this information into our IDEA Statica checkbot application. So all I have to do is just click on select cursor and select geometry cursor. So if you have, for example, you have a very big structures like massive high-rise building, you have the options to select a portion of the structure. So if, for example, you want only to select that one, that's perfectly fine as well. However, we have a kind of like a small structure right here, so there's not many members and there's not many nodes, so I can just basically select everything from it. So here, I just have to go to utilities, click on user tools, and then again, I will click on IDEA Statica checkbot. Once I click that, it will open up checkbot application. So let's just give it a few seconds while the program is opening in the background. Okay, so it's coming here. Okay, here it is. So I now hit here. So it opens the checkbot application from IDEA Statica. Now I have to select the design code. So earlier, Engineer Jarrett has selected design code AISC 2016. So I go back to my checkbot files. I have to select American code, which is AISC. I'm going to change it to 16. And the concrete code, I'll just change it to 19 in this case. So I'll have to do is click on create project, that I will have my checkbot files available. So from here, the program isn't captured yet. I mean, the members isn't captured yet. So all I have to do from here is click on connection so that all those available members will be transferred directly into our program. So all I'm gonna do is click. All gonna be imported. No? Okay. So right now we have this program available. So let me just turn it on. So here you can see that all information are being captured from STAAD.Pro. And if I go to the loadings as well, so you can see that every single loads that was added by Engineer Jarrett has been captured by IDEA Statica. And the good thing about this is that when you design connections, you don't have to manually encode the internal forces or the envelope forces, no? So you just have to, the program itself will automatically capture that for you. And there will be some issues if you, for example, you do it manually. There will be some time that, for example, you might made mistakes on using the sign conventions. You might possibly say, okay, I put in positive moment when in fact it could be a negative bending moment. So when you use this kind of applications, it actually mitigates that kind of problems, no? So from here, all I have to do is just click on cancel. So I leave it as it is. Then cancel. And right here, also you have the options to look into or to draw the internal forces diagram. So here, you have here, I can show the axial forces. If I just click on wireframe view. And I can also show the bending moment, for example, there. And of course, the good thing about that is if you can follow the joints right here, the programs automatically group the joints for you. No? So what is basically automatic grouping? So let me just share my slides. One more thing. When the program groups, so it actually automatically organizes the connections into a specific project tree into separate levels like typology or cross section. So when you say typology, it considers the number of members and the relative positions. For example, beam to beam or beam to column. And if you have arrangements like topology and cross sections for both, then within the same topology and connections are further grouped according to cross section. So with this is actually with the lowest similarity that is required to basically enable searching for something like similar design from our connection library that you can make use of. So let me end that right there. So this is basically group for now, but in our case, we still need to do some adjustment right here, no? So you see from here, in IDEA Statica, it captures everything STAAD.Pro has provided. And for example, here in STAAD.Pro, these members are actually modeled as node to node, but in actual fact or in actual conditions, this can be continuous member. So what we can possibly do is that we have the options to merge this member. All we have to do is click on merge. And you have to do that for the same types of members. No? So the same thing here. For example, in actual condition, we don't usually put our tension rods at the apex of the rafter. So you have the options to offset this as well. So for example, right here, I just want to offset here. So for example, 1 to 0. And at the same time, I also want to put this down to minus. I already know the distance here. I'm putting it at the center, and the same goes to the other side so that it will be added. Now I need to do that in every single members right here, no? In every single members of the structure, so that when we try to do the modeling in the connection applications, it's already specific into that desired connections that we want to do. So instead of doing this right here, and to make it more save us a little bit of our time, I already prepared a merge model for you guys so that you can already see what is being done. So here, every single members are already merged, and all the eccentricity I've also provided right there. So in order for me to design the connections, I have now the loadings available, basically. So I have the options to select every single groups right here, whatever I want to design. And I just want to say also that in each group, there is a number of nodes or number of joints, perhaps. So, for example, this group 1 right here, this is basically this nodes right here, and in each group there is actually a node called a reference nodes or a reference connections, and from that reference connections, this is where you are going to create your connections, and from there other members of that group will follow that reference connections. The other members is called child connections. So whatever manufacturing operations you apply into reference nodes or reference connections, it will be easily copied into the child connections, so that it saves time in doing the analysis. Now you don't have to model every single connections for the rest of these things. No? And when you do the analysis, you only have to analyze it once. No? So for example, here, I have here, for example, if I just say, let's try to do design here, this chevron bracing. This chevron bracing right here is the joint where the gasket is applied. So here we have the options as well to, so let me go back. Here I mentioned that there is plenty of loads combinations available, and there are hundreds. For example, some projects have hundreds of it, and even some big projects even have some thousands of those combinations. Here, in IDEA Statica checkbot, you have the options to just tell the program to calculate the load extreme. So for example, here, I click on calculate load extreme. The applications will actually select only a number of load combinations that the programs identify as extreme combination. So for example, here we have a node or joint 60. There are 7 critical load combination or critical load effects that it will use. For 59, there are 9 critical load effects. So it actually saves you some time when you try to analyze this thing, these joints for you. So here, for example, I want to design all those joints, perhaps. So all I have to do is open the reference connection. And when I open reference connections, another applications from IDEA Statica will open up, and that will be our IDEA Statica connection application. So let me just it very quickly. So okay, here. So from here, you can already see that this chevron connection here from the chevron bracing is already captured. And when these load effects are already captured, you can see that each check item, these are the one that the program considered as a critical load combinations or critical load effects. Now, if you want to say, okay, I don't want the program to select, I want to select everything. So you can just, from the checkboard, you can just say that I want to select everything. Huh? So from here, for example, I want to design now the connections. So what I can do for now, I can use our connection library. I can actually do this manually, do modeling manually piece by piece, but we can, but to save us some time, basically, we can just hit or make use of our connection library instead. Manual modeling can be do some other webinars for that topic now. So here, all I have to do is click on Propose. And IDEA Statica will, based on the typology and geometry of your structure, it has its own library of connections that can possibly use from this specific connections right here that you can make use of. Here, I have some parametrics and I have some different shapes as well. But this one right here, I have here specifically prepared despite connections. So all I have to do is click on OK. And same thing from here, all those joints, all I have to do is click on OK. So now all those connections are, or all those, like for example, the gussets, the plates, the bolts are already added from your connections. No, you can run the analysis from here. You can also do that. You can hit calculate, but in my case, I'll just have to save this and close it. So I will calculate it from checkbot instead. So I can just hit on calculate from here, hit on calculate all, and whatever informations that was created from our reference connections, the child connections will just copy that specific joints itself and make use of that critical load effects that is applied from its own joint. No? So I don't have to wait for this, basically. I can let the program run for that. And in my case, I can just do another group, perhaps. No? So for example, I want to design the pedestal for this main structure right here. I want to see which group is this. So if this is group is actually under group 2. So for example, I'm going to leave this calculate load extreme as is. So I'll just click on open reference connection. And again, it will open up my connection application. So right now, while we are waiting for that, you can see that some nodes of the group are being calculated and one joint is already passing. So here, okay, from here, we now have this connection. You can see that it's there, a bare connection. It's just a members. No, there's no connections from here. When we open it, we need to apply specific connections as well. So here you will realize that all of these are checked, and that's because we didn't select the evaluation of critical load effects. So all of these loads are being added right here. No? So for us, all we have to do now is just apply the specific connections that we want to do here. Okay, so once again, I'm gonna click on propose. So there are various members or various connections that are available depending on the shape of your structure, basically. So I can make use of the templates that I have created, or even not just the template. You can, if you have predefined template from your company or your colleagues has created some templates for you. If he is a member of your company license, you can make use of that template as well that he make. So here I have my own template that I can use. So I can just say, okay, you can click on OK. And again, click on OK so that it will be applied to my joint. And you can see that there are some, all of the model for my concrete pedestal has been added, as well as those anchorings. So here you can see that all the operations is also added. So basically you are ready to run. There are some notifications right here that some welds were changed to complete joint penetration instead of fillet weld. So here you don't have to worry about that. The program automatically changed the operations for you when it comes to weld connection. So for example, this is actually modeled as a shell the application behind when you try to analyze these members. This is actually a shell element. So when welding into the edge of the shell, it's not possible. So it has to be converted into a complete joint penetration. So here, I leave the program as it is, if you want to. But if you want to have this warning available, made changes, I can basically change this to, say, for example, instead of using a fillet weld, I can just make use of complete joint penetration weld as well. Well, so we can do that, and I can just say save the file, and I can now close again, and from here I can also hit calculate and everything. Now, to say something that we need to analyze everything. So for sure, you know the procedure already, how to do it in this case. So we have everything like the internal forces, and we have all the groupings. So obviously our task is to apply all the joint connections and design everything. So I don't want to show that the whole process to you guys, because it's the same in every single group. No, so with that, I already pre-prepared some the complete structure for you, where the connections has been totally designed. So here you can see that every single group has been analyzed, and you can see some green check mark. It means that it's code check pass. And if you see a green X mark, it means that it's code check fail. So there are in a specific group, like for example, group 1, there are 2 nodes that is passing, but some are failing. And you can see from the results right at the bottom corner, is actually most of the design is considered to be verified, like the welds, concrete blocks. But here we have some failures on the anchors. And the same thing if we choose for group 2, because for group 2, under group 2, every single joint is actually failing right here. Now we need to investigate what is the failing. So from here, you can see that the plates are also verified to be correct. Code check pass. But you can see that all the anchors are failing. So let me just check every single nodes or every single joints, and select which member is the most utilized or the overutilized joint. So from here I can see 347, under 19 I can see 362, under 349, 360. So basically under node 19, which is somewhere right here, this is actually where our maximum utilization occurs, where our overloading occurs. Now I can open this file to investigate further. Click on open. While it is opening in the background, just open the file. Wait for a second while the program is opening. Okay, here it is. So you can see that the overview of the verifications right here is every single verifications. You can see that this code check pass, except for the anchors. Now, if I go to the check tab to investigate further on that anchor, I can just say go to the check tab. Okay, let's wait for a few seconds. So let's see. I hope the screen isn't frozen. All right, there it is. Luckily, it wasn't frozen. Okay, so now let's continue. So let's go investigate this further. I want to make it much bigger. Okay. So here, you can see that the anchors are actually the one that is failing. No? So there are number of anchors right here, A1 until A8. So, but from this utilization, you can see that 262, these anchors is under 262. So if I just investigate these specific anchors and click on print preview to check which kind of failure this one is going through. No? So here, anchor tensile resistance is basically okay. Our demand is less than what we are. So from here, we can already see that concrete breakout resistance is actually the one that is failing. No, it's less than the demand. No, the capacity is less than the demand, and the rest is okay except for the concrete breakout resistance. And if we go to the interaction of the tensile and shear force, we can see that, all right, this is some sort of like a 3.62 right there. So I can click on close to this one. And I want to say that why this is failing. The reason for this is that when the program analyzed, it uses the code requirements, which is based on the codes. When we check for anchoring, basically the concrete is basically considered as unreinforced concrete or plain concrete, and that is why when we design such connection or such anchorings, or one way we always do when we follow those requirements is that when we see it's failing, either we increase the size of the concrete. In our case, this is a pedestal, but we have the options actually to make use of the reinforcement itself. No? So in my case, I don't want to increase the size of my pedestal. I want the same shape. No, so I'm going to make use of my reinforcement. In this case, we can basically forward this into our IDEA Statica detail 3D. So here I can just click on RC check. When I click on RC check, it will open up. It will ask me to save. So for example, I change this to and name it to, what node is this? It's 19. So I'm going to save it as 19. I'm going to click on save. It will open up. IDEA Statica detail application. So let's wait for a little while. What is it being opened in the background? Okay, here it is. Right. Okay, comes a few seconds. Okay, here it goes. So right here, whatever the program from our program is copied, because we are using the code ACI. So you can see all that information from our anchorings has been captured into detail 3D. You can see I'm now in a different application. It's no longer connection, but it's already IDEA Statica detail. So from here, I can basically apply reinforcement because all the information, such as the loadings, has been already captured. You can analyze the same loads exactly as what is being here. But if I go back to my to our connections, I can basically say that the maximum utilization occurs is actually under load combination number 39. You have the options to do everything for that, but for this specific demonstration, I'll just deactivate all of it and just consider load combination 39 just for this specific demonstration because I want to save us some time. So from there, I want to say as well that we need to review some of the supports necessary. So here, I need to change some parameters right here. This is a pedestal, so this should be connected into some sort of a foundation or a footing. And I want to deactivate this compression only spring support so that the forces will be transferred into the forces will be transferred to my foundation. So now I'm going to select as well the anchorings. So from here, the anchorings, you can see that since we are using American code, American standards, by default is actually using imperial size of reinforcement. So this is from here, it actually reads as number 8. So bar number 8. And I want to change this to user input. And instead of using bar number 8, I want to use metric unit. So just click on this part right here. Okay. I hope it doesn't freeze. Did not freeze. Okay, wait. All right, so I leave this as grade 60. Oh, sorry, wait. I hope it's not frozen. Okay. I just give it a few seconds while it's still running. Okay, here it is. Now I change the diameter to of the anchors to 24, and I'm using M24 right there. And from here, I can just say I want to put in my reinforcement for now. So that should be made available. All right, wait a second. No, there. Okay, so there's a number of applications open in my program. So just bear with me for a second. All right, now there it is. And from here, I'll just say I want to put some reinforcement, the rebar. So I just click on group of bars, and I want to apply the reinforcement in this case. So let's say I'm going to make use of diameter 25 reinforcement. So diameter 25. And I'm going to change the reinforcement to, for example, right here, I'm going to select the surface where I want to put in my reinforcement. Huh? So here, I will use, instead of surface edge, I'm going to make use of surface edge on more members. Huh? So from here, let me just say, this one is selected, but I don't want surface 1. Okay, let's say I want to use surface number 2. And from here, instead of using edges 1 and 2, you can see here, this is edge number 1, and this is also edge number 2. And we have here edge number 3, number 4. Now I want to place my reinforcement at edge 2, 3, and 4. I'll click on OK. You see my reinforcement will be some sort of like that, like a U shape. And of course, I want that reinforcement to go all the way to the ground. All I have to do is just make that anchorage at the beginning to be continuous. Okay. And the same thing I'm going to do at the other end. So it's going to be continuous. And you will see these arrows over here that represents that my reinforcement is actually continuous from there. So from here, I can just say, okay, the surface cover to be 40. And I will apply some number of layers to be 5, for example, and change it to 110. Okay, so from there, I have that specific layout. So okay, let me just put some edge cover over here. I want to say, I want to have a cover of like 40, 65, and 40. So it will make some adjustment like that. Yeah, right. This is a hypothetical reinforcement layout, but you can also do your own specific layout should you want to do it. Now I can copy the same thing. And from there, I say, all right, I want to change it to surface number 1 instead. No? So that specific reinforcement will be also copied. But of course, I just need to, I don't want to have some overlap. I just need 3 over there. Then I need to change the spacing, for example. And here, I want to change it to 150. Right, so I can also change the, what you call that, the covers right here and just say 40. And I can also save. From there, I now have my reinforcement. And I say, okay, I want to put some ties or stirrups or column ties. Or pedestal ties, I should say. So I can just say, okay, I want to use ties for 10 mm. And of course, for that, I need to select my surface as well. So here, I need to put it under surface number 6. And of course, instead of 3 edges, I want all of the edges. So I'll just put the missing edge over here to be 1. And just I can see that all my information I have. Of course, I need to put some bend over there. It's not going to be continuous. All I have to do is change to bend over there. And I can change the spacing as well if you want. So from there, let's say I want to put 50 mm from the edge or from the color. I can just say spacing of 50. And from there, I can just say cover to be 30, for example. Then I'll have that one. Okay, I need more, perhaps. Let's say 9 pieces, for example. All right. Now that I have everything, basically, I can actually now run the calculations, perhaps. No. So in order for us to check that everything, whether this anchoring is okay or not, then I can click on calculate. So if I click on calculate here, it will run the analysis. Of course, to save us some time, I already prepared that analysis for you, which is already here. I made that results. So as you can see, all my results from previous one, if this is overloaded by or overutilized by 362%, now it becomes 99% right there. So you have the options to go into the check tab to verify further our results. So here you can see the stress flow of the anchors. You can visually see, okay, what is going on inside the anchors now, inside your concrete pedestal. And if you go to the strength tab, you can say, okay, I can also see forces or the principal stresses. And you can even see, for example, not just you can also see what is going on inside, not just the outside stresses. No? You can also see that what is going on. Okay, so you can also have, if you go into the reinforcement, you can see also what are the stresses on the reinforcement. If you go to anchorage, you also can see that from here. Right. So now that we already know that all of those informations are fully verified, all our anchors are fully verified. We don't say, okay, I'm no longer afraid of this because we have verified this to our detailed applications. Now I can actually create IFC files from all these connections that we have that we have analyzed, and share these connections into any CAD software. For example, here we are using TEKLA Structures. I can share that IFC file to TEKLA Structures, and all I can do is say, okay, I want to select, let's say, for example, I just want to select the apex of this, okay, for example, here until here, or let's just select, for for example, this group right there. So you can just say export to connection and or perhaps RFC. IFC. You can select on IFC, and you have to save it now. So every single connection right here can be saved into an IFC files and forwarded into TEKLA structures. Now I already export all of this into an IFC files to save us some time. Now let me demonstrate it how we can do that in TEKLA structures. No? So let me just close this extra right here. So this is the model from our TEKLA structures, and what we can possibly do is from this application right here, I can just click on add model under reference models. You can do that here as well. Import, or basically here I can just do that from here this side now. So here if I can select add model, and I can just browse for that specific file where I save it. So for example here, I already saved all those information. So like for example base plate plus pedestal, I can just say open. But just want to highlight as well that our model came from STAAD.Pro. We designed this, we analyzed this from STAAD.Pro. So in STAAD.Pro, let me just show this model again. Oh, sorry. In STAAD.Pro, there is the model of the axis is basically in the what you call that the vertical axis. Oops, sorry, what's going on? So here you can see that the vertical axis is actually in the Y direction. And in TEKLA structures, the vertical axis is actually in the global Z. So what we can possibly do, because the geometry coming from checkbot is the same exactly as what is being modeled in FEA analysis. So what we can possibly do is just rotate this by 90 degrees and click on add model. In the add model, you can already see that, okay, all those connections from IFC files has been captured. The same thing if I add all those from, let's say, another file right here. I can browse, for example, I want to add the chevron bracing over here. All I have to do is just click on -90 so that it will reflect from coming from STAAD.Pro, and I can click on create model. Okay, so you can see from here, it's already being captured. No? And when I write in this to TEKLA, Engineer Dennis will look into this model. I think I have provided him some IFC files as well that he can use. He has the options to make use of the IFC file as a reference file. He can measure it by himself if no matter how he wants it. Or some for example, some plates or operations like the ribs, for example, you have the options actually to convert this into a native TEKLA component. Just remember, it's not all can be exported into a native TEKLA component, but only some specific plates, not every single component of it. So what I'm going to do in order for Engineer Dennis to make use of these files, now what I can do is I can write out this one so that he can read it as well. I'm going to save it. Oops, sorry. I'm going to save it once more. Okay, let me just close this thing. So let me save it again, and I'm gonna write it out. Yes, save it, and it's create a bucket. Okay, so I'm gonna give this to Engineer Dennis. Thank you very much for your attention, and I hope you learned something about it. So, Engineer Dennis, the floor is
Okay.
yours.
Yeah, thank you very much, Engineer Jean. So again, going back to TEKLA structure. So everything has been designed and the sizes of the members and even the connection. So can you see my screen now?
Yes, sir. Go ahead.
Okay, good. So now, to save again our time, because I think we're already over, it's already over time. So this is what Engineer Jean created earlier. So the gusset plate, the girts, the base plate, the hunch, I already read in that one. So as you can see, it's already here in my system. Now, the first thing that I'm going to do is the base plate. So basically, like what Engineer Jean mentioned, is we can either you convert this one to IFC, but you need to do some manual thing. But basically, TEKLA structure has this component available in the system. Let's say, for example, I just simply type here base, and then opening this stiffener base plate connection. So as you can see here, I already created the IDEA Statica parameters here, wherein I follow already all the plates and web and flange just here. So basically, if you have already the PDF file from IDEA Statica, all this information, what you can do is just simply get that information and then put it in here in the parameters, or else you can just simply click this one and then get this one. As you can see, 25, I put here 25, and also maybe the distance size of this one, and then you can put that one on the bolts spacing, 450, something like this. Then once you have this, I will just simply apply this one. And then all I have to do is to pick the column and then use the reference and then pick this position. So as you can see here, it will mimic the IDEA Statica connection. So if I turn off my IDEA Statica IFC, then this is the yellow is created by TEKLA structure. Now, if I want to apply those base plate to all these column, all I have to do is to select all the column, and then again, from the IDEA Statica base plate here, I can just simply pick a position, and there you go. So you have all the base plate for all the column here. And then if you want to add also the column base plate on this, the base plate on this column, smaller column, same thing. I will open this IDEA Statica IFC. I will use the base plate 1004. Again, here I specify I created the attributes for IDEA Statica. Then same thing, apply, and then OK. So select all the columns, and then pick the position of the reference, and then there you go. So you have now already all the columns base plate created. Now, let's move on for the connection. I'm not going to take so much of this time, because in TEKLA structure I created already all the auto connection. So by the way, earlier, if you notice here, if you inquire the attributes, you can see the end condition here. This one is useful also when you are creating the auto connection. Under this TEKLA structure, I have this auto connection setting. At the moment, I set up the IDEA Statica just to show you that one of the condition here, if you create the rule, you can use the here, as you can see, you can use the secondary shear force, axial force, bending moment, and so on. So meaning all those information, you can use that one in creating the condition for the auto connection. But at the moment, I uses the name to make it simple. So what I will do now is I'm going to select everything. Okay, sorry. By the way, let me just show you first the gusset plate, this one, the girts connection, the apex connection, and then the hunch connection, this one, right? So all this connection, I created an auto connection according to the IDEA Statica information. So what I will do now is I'm going to select everything. So in one click of a button, instead of adding the connection one by one, all I have to do is select the IDEA Statica connection here and then create connection, and that's it. So you don't need to go to each and every joint to add this connection because the system will add this one for us. So as you can see here, this is the connection created according to the similar to the IDEA Statica element. Also, going back to what Engineer Jean mentioned, if I have this chevron gasket plate like this, so look at this. This one is also possible that I can select this element, this element, this element, and then I can just simply convert to IFC object. So basically, if I select this convert to IFC object, this one is not a TEKLA structure element. It's an IFC, but here I can just simply convert this one as maybe as an extrusion, and then apply changes, and then close, and there you go. So once I close my chevron gasket plate, there you go. So this one, all I have to do is to go to my weld, and then select the welding so that it will be part of my assembly. So later, when we create the drawing, that will be part of the assembly drawing. Okay? Now, to continue, I can also open my the roof brace. So this roof brace, remember earlier, Engineer Jean moved that one to the center. So all I have to do is to select again the roof brace and the rafter, and then hit create connection, and you will have this connection similar to what Engineer Jean created in IDEA Statica. So same thing, there you go. All right, and done. So I have already finished my connection here. Now, going back to the drawing that I have created, if I open the drawing first, okay, before I create the whole erection drawing, I just want to show you what happened to the drawing that I have created earlier. So remember, from UB 351, this one become UB 457, and then as you can see, automatically there will be a cloud telling me that there's a change on that particular profile. And then as you can see, even the connection automatically change here in the drawing. So the drawing is always updated. Once you update that one in the model, in TEKLA structure, the drawing is always updated. Now, let's move on. Okay, since I have a little bit of time, before I create the drawing, let me just show you also another option. What if you want to add a railing? So this one will not take a minute. So here I have the stanchion railing. Apply and okay. So all you have to do is to pick this point and this position. This one is just an additional 1, 2, 3, 4, 5. So meaning all the stanchion will be created on that particular. So here, as you can see, the railing is already created. So if you have a miscellaneous item in this building, you can also add the railing. Now, once you're done with that one, I can just simply run the numbering. So numbering means the system will automatically assign the piece mark for every element. All right? So no need for you to assign the number. The system will take care of that one. So what you can do now is to create the general arrangement drawing. So let's say 3D, level 1, and grid A. And then select open drawing. Then I can select a sample template here, erection drawing, apply, and okay. Now look at this. To create an erection drawing, you don't need to draw it one by one. So this time, if I hit create, now hands up, because the system will create the drawing for us automatically with all the annotation and even the dimension for the grids. So here, as you can see, there is annotation, the dimensions are there. Okay, so everything has been created. Okay, and if you want to have additional information, let's say here, I want to create a detailed view. So you don't need to, again, to draw. So automatically the system will draw for us. Okay, if you want to get the section, you don't need to imagine what it looks like. Sometimes the drafter has a very poor imagination, then you will have a big problem if your imagination is very poor because the drawing will be totally conflicting. So here, automatically, the system will create this section for us. If you want to add the dimensions, you may do so. Just simply click this position, this one. Oh, sorry. Then here, if you want to add more, you can just simply add the point, and then you have now the dimensions. So something like this. Okay? So these are simple manual things that you can add. And then annotation-wise, you can simply select all the object and then add mark. So you don't need to type the annotation because here automatically it will give you the piece marking. Now, if you want to change the piece marking instead of part position, you can also add the name or even the profile here. Sorry. Let's say here you can add the profile and then modify. So you have P16 and these are the profile. So quickly you can create your drawing in TEKLA Structure. Now, if this is the erection drawing, now if I may, I can now create the fabrication drawing. So what is fabrication drawing? Fabrication drawing is used for the fabrication. It will create the assembly drawing. Let's say I'm going to open the master drawing catalog and then open my document manager. So document manager, this is where you can see the drawing that you have been created, okay? And then the master drawing catalog, let's say I'm going to select drawing creation. This one, I create the rules to create the drawing for column, beams, and rafter. So I'm going to select, let's say, a couple of column here, one rafter here, and then one beam, or maybe two beams, okay? So look at this. Once I hit create drawing, so the system automatically create the drawing for us. Imagine if you're creating one assembly drawing for your fabrication. It takes 2 hours, maybe 4 hours, maybe 1 day to create one fabrication drawing with all the dimensions and all the bill of material. In this case, I selected a few members and then started the 403. So let's see. Maybe it will take 2 minutes. That's good enough. But I guess it will be less than that to create 5 or 4 drawings. Yeah, 5 drawings for this. So this is how the system really help us. So you will save a lot of time in creating the fabrication drawing. Not only that one, just to add on, not only for the steel, of course, for the if you have a concrete part, you have the reinforcement, automatically the system will create the bar bending schedule. So at this time, it will only create the assembly drawing that will give us all the piece mark, all the dimensions, and all the bill of material. So yeah, so now I think it's around a minute. So imagine 6 drawings within a minute. So let's open the column first. Look at that. So look at the column presentation. So I can make it black and white. You have all the dimensions created automatically. You don't imagine if you're going to add the dimensions one by one, how much time it will take for you. And the best part is this, the bill of material calculated automatically. If you're doing it manually, then once you finish the drawing, you have to calculate one and each and every element to put that one in the bill of material. Now let's open the beam. So this beam as well, as you can see, you can change the color as well. So here, automatically, it will create the part detail, all the dimensions of each part. Okay, remember, this is the IFC converted to TEKLA structure element. And this one is also created here in the bill of material. So what else? Let's say the rafter. So this rafter, okay? So all the parts are created. This is the gusset plate for the bracing. This is the end plate, and this is the bill of material. So everything will be created automatically by the system. And again, like what I've said, I'm always telling you will save a lot of time if you're going to use the system for your fabrication drawing. So now that we're done with that one, I just want to add also we have the report. If you want to get the material assembly part list, this one. So if I select create from all, imagine if somebody asks you the report, hey, can you give me the total bill of material? This one is one click of a button, maybe a couple of seconds. You will get all the bill of material here, and then it will tell you the total assembly and then the total weight of the structure. Not only that one, if you want to get the I don't know if I have the report for the bolt. Yes, let's say a bolt list, bolt site location, create from all. It will give you the total number of bolts. These are the quantity of the bolts, and then where it is connected. So it will give you this information using this TEKLA structure. So I guess that is my part, modeling, creating connection, and creating the drawing. And basically, this is TEKLA structure in the nutshell. If you have any more question, you can always contact us. Now, I'm going to send it back to Engineer JP for the conclusion of our presentation. Back to you, Engineer JP.
Okay, so let me share my screen again. Actually, we're already on Q&A. Wait a second, let me just share my screen. Okay, can you see now my screen?
Yeah.
Okay, so it's already Q&A part, no? But by the way, so thanks to all the speakers, no, Jean, Dennis, and Jared. So I think we can attend, no, some couple of questions. So feel free to send your questions on the chat box, and we will try our best to answer those. Okay, so there's there's one question here. No, I think this is for Jean Valiente. Is there limitation for size of model in IDEA Statica? Would it be able to import a super tall building, for example, with thousands of connections?
Okay, thank you for that questions. This was a good question, perhaps actually. So
I think
in
Ahmad
IDEA,
is attending from the Middle East, right?
oh yeah, it's from the Middle East. Ahmed, okay. Thank you for that question, Ahmed. Actually, super tall, you can consider super tall probably like high-rise structure, and perhaps there's actually no limit as far as I'm concerned. We've imported buildings, but you can only export it 1,000 nodes at a time. So meaning you can put in number of joints 1,000 nodes at a time. So whether you have 5,000 nodes or how many is it, you have the limit to export it once at a time, basically.
Okay.
So I hope that answers your questions. Just keep it coming. You have some more?
Yeah, I think there's one question coming from Kirby James Asuncion. He's raising his hand. Or Kirby, you can type your question on the chat box. Okay, so I will add one more question here. Is it possible for TEKLA to produce drawing solely, no, in the steel connection without the global model.
Uh, Global model meaning not creating the whole model, right? Is that
Uh,
is that correct?
Question coming, yeah, from Alexandrio. Yeah, okay. The question
So
coming from
is that
Alexandrio.
means that you don't want to model the whole the whole structure only for the connection? Is that right? Oh
Yeah,
yeah,
from the
yeah,
chat
oh
box,
yeah, just the
he
connection.
said yeah.
Yes, of course you have to model the connection, and then you can create the drawing anytime, anytime. Even without any model, the TEKLA structure can create the drawing for the what do you call that, erection drawing. Yeah. But of course, you need to have
Okay.
a model at least that to create the assembly or the part drawing.
Mm.
But you don't need to really to create the. Okay, in Singapore, one of most of our okay, maybe not most, some of our client in the HDB precast company. So they don't model the whole HDB building. They model per cast unit, per wall, and then they create the drawing out of it. So it's possible. Okay, I think it's I think it's time. Sir JP, I think
Yeah,
you can share their
yeah,
our contact to them, and then if they have
yeah,
any other
yeah. It's
question, they
already
can
yeah.
contact us
Correct,
also.
correct.
Yeah.
Yeah, so we will try. We just get all your questions, so we will try to answer that no on separate email, no. Because there's so many questions now, no, coming in the chat box. So we're gonna be ending now the webinar, no. But before that, we have promotion coming, no. For those who want to buy Idea Statica here in the Philippines only, no. So we have promotion of we have discount of 40% off, valid until October 6 only. So if you're interested, feel free to contact us.
Wow, nice.
And yeah, so we hope this webinar no, has provided you with valuable insights. No, we would be truly grateful if you could take a moment to share your feedback by leaving a review on our official Facebook page. No, what you are seeing on the screen. Okay, so then so on behalf of X Structures, Trimble, Bentley, and Idea Statica, I would like to say thank you everyone for joining today's webinar featuring TEKLA STAAD.Pro and IDEA Statica. We hope this session has given you valuable insights into how these powerful tools can work together to streamline workflows from modeling and analysis to connection design and fabrication. A big thank you as well to our speakers for sharing their expertise and to all the participants now for your active engagement. Let's continue to apply what we have learned today to push innovation, accuracy, and efficiency in structural engineering. We look forward to seeing you in our future trading sessions and event. Thank you and have a great day ahead. Maraming salamat po.
Okay, thank you very much. Bye bye.
Thank you.
Thank
Thank you.
Thank
you. Bye
you.
bye.
Thank you. Bye bye.